All right. Well, thanks everyone for joining us for Virtual Lab Notes today. It's February 24th. We're really excited to have you here, and we're excited to have Dr. Neda with us from the Department of Mathematical Sciences at UNLV. Just a few notes as we get going. Make sure that your microphone and it stays muted and your camera stays off throughout the duration of the presentation. It helps with the bandwidth and it helps to eliminate any interruptions. Make sure those buttons at the bottom are both red. You can use the chat function if you have any questions throughout the presentation. Feel free to just pop it in the chat. We'll get to questions after Dr. Neda's presentation. So if it comes up while she's talking, just throw it in the chat and we'll get to it a little bit later. We'll try to end about 12:45, 12:50, so we have time to answer all of those questions. If you have any issues with Google Meet during the presentation, make sure that you visit the Google Meet Help Center. It's that support.google.com/meet. And then also today's presentation is being recorded. So it will be available on the College of Sciences website after the presentation, and also be available on our College of Sciences YouTube channel. So you can check out this lecture, plus all the previous lectures at the UNLV College of Sciences YouTube channel. Before we get going, I just wanted to also say, save the date for our next virtual lab notes. It will be with Dr. Bing Zhang, who is a distinguished professor and the Associate Dean for Research in the College of Sciences. He teaches in the Department of Physics and Astronomy, and he'll be discussing his research that was actually just published in, I believe it was Nature magazine a few months ago on fast radio bursts. So the topic is fast radio bursts, a mystery being solved. So if you're an astronomy buff, it should be a fascinating lecture. And with that, I would like to take a moment to introduce our speaker for today. So Dr. Monika Neda is a professor in the Department of Mathematical Sciences at UNLV. She joined UNLV in 2007 after completing her PhD at the University of Pittsburgh under the guidance of Professor William Layton. She's supervised PhD students, master's students, and undergraduate students on research topics related to differential equations and modeling. Dr. Neda's expertise is on computational fluid dynamics and numerical methods for partial differential equation. Her research focuses on the theoretical and computational studies of fluid flow models that are based on Navier-Stokes equations. And these studies include derivation of the energy inequality, models microscale, finite element analysis, sensitivity computations, and simulations of fluid flow problems. Despite a strong interest in applications, Dr. Neda's work is still quite mathematical, but it's very interesting, so I'm excited to hear it. And more specifically, she is still a mathematician who proves theorems, but for the purpose of solving practical problems faster and more accurately. So we're excited to have Dr. Monika Neda with us, and excited for her presentation on mathematical modeling. How can we predict fluid flow? And with that, Dr. Neda, I will let you take it away.
Thank you, Corey, for such a nice introduction. So thank you, everybody, for coming. So I'm going to try to present. I assume we can now see the presentation and we're good to go.
We can see it.
Thank you. So as Corey said, it will be about mathematical modeling, and the main part is about fluid flow. An outline of the talk is I'll start with some background about mathematics, then I'll go into mathematical modeling, the ideas behind it, and then I'll dive into the computational fluid dynamics, which I really believe can resonate with the general audience very well. And I'll present some of my research results about numerical analysis and computations in this area of fluid dynamics, and I'll finish with some conclusions. So with that said, what is math? And I'm sure you all started studying it probably somewhere like in kindergarten or even before that time. So you all have your definition of math. And you are welcome to type something in the chat just for fun, your thoughts on it. Now, What can I say? Well, this is something that I came across over the years, trying to answer to that question, and answers that I got from students, members of the community around me, and so on. So it's used in science, it's solving something, and it's definitely hard, students would say that. Keeping all this in mind and so on, I'm going to start with this quote of von Neumann that once said to Smith, "Young men in mathematics, you don't understand things, you just get used to them." So this quote was really in response to Smith's fear about the specific topic in mathematics, which is the method of characteristics. So hopefully by the end of this talk, we're all going to get used to these symbols and to mathematics overall. Now, leaving that on the side, what really math is? So from Britannica, we have this definition that when we look at it, it has so many things. But if we just take one step back, it's clear that math is all about structure, order, relation, that it's backed by logical reasoning and quantitative calculations, how mathematics is indispensable to physical sciences and technology, and in the more recent years, even to life sciences. Now, from where the word really mathematics comes is from our Old Greek, ancient language, mathema, which means that which is learned or what one gets to know, study. So the roots of mathematics are really lying in this Greek civilization that many years BC started to work on all these different topics that we're still even using today. Okay, so with that said, I'm going to go into this mathematical modeling that, as I said, I think resonates with the general public, and it's connected with every corner of science that you probably have been studying. So what are really the steps, the main steps that we have here in the process of the modeling? So the first one is that you define a problem, or simply a problem appears to you and you need a solution for it. So we're trying to do this systematic approach where we're going to break down this complex phenomena or process that we have in nature or in other different, industrial applications, and then try to find a solution for it. So having your problem, you're going to try then to identify your controlling factors, and this can be, very complicated, and you're probably never going to be able to do justice here and go to some perfection, but the best it is done, the model will be better. After that, we evaluate the data. So we have some data. So in my modeling, I usually work with data such as initial conditions, boundary conditions of my problem, or simply some data about parameters and so on. But this, depending on the modeling, can have a different meaning. And it can be, even more work, elaborated work, and so on. So after that, you're going to construct a model. So you're going to come up with this model. It can be just a simple equation, a linear equation. It can be a system of differential equations that I'm going to present later today, and I'm going to connect them with this pandemic that is all around us. Or it can be a system of partial differential equations that I will also present one, and that will be related to the fluid dynamics and to my main research. So after we have this model, we're going to try to solve it. So now you have different methods, depending what model you have, what tools from mathematics that you can use to solve that model. And after you solve it, it needs verification. So, sometimes this solution will actually even include coding, programming. So after all this is done, you need to verify your code. So you may need to go back, debug, go back to the construction of the model if things are not working. And if the verification goes well and it's done, then you go into the validation. So you're going to validate your model. Usually you're going to use experimental data here, and you're going to check that what the model predicts agrees with the experiments that are known, and after this is done, then you would say that you have a good model for whatever problem you had at your hands. So keeping some of these steps in mind, I'm going to try to mimic them quickly to a very simple problem here, which is simply just finding a function that models your electricity bill. So Nevada Power gives us one every month. So they have some functions that they use, some model, they plug in some inputs, and they're going to go, going back and getting us the bill that gets mailed to all of us or emailed. And this is a very simple one here. They have a much more complicated thing. But let's say, we have a charge of 11 cents per kilowatt hour for electricity, and we have a $15 of this basic connection charge one-time fee. Well, then this can be modeled with a very simple linear function, a line. So we have 15 being our y-intercept, because when x is 0, so you did not spend anything, you still have to pay the $15 connection fee. And then as you start spending, x is your the kilowatt hour electricity usage, you multiply by 11 cents, 0.11, to really get then the total amount of charge that will be in terms of this x of the usage. So this function has this slope, what we would say mathematically of 0.11, this change with respect to of y with respect to x, and it's simply a line, a graph, very easy to understand. Now, let's move on to something a little bit more sophisticated, and this will be the basic SIR model, so known, which is now so much talked about it, and there is so much in the literature about this model, since this is the classical model for modeling the spread of a disease in a population. So we have now this pandemic, COVID-19, so this would be a classical model to see the spread of the disease of COVID in a population. With that in mind, the members of the population are going to be, categorized into three groups. We have the group which is the susceptible, usually denoted by S, then infected, denoted by I, and then recovered, denoted by R. So then if I add my three groups, S, susceptible, infected population, recovered population, I'll get the total population. Okay, so now since I really want to see the change of these groups, the change of the susceptible, the change of the infection population, so is it going up, going down, the change in the recovered population, what we do in math, we take the derivative. So the derivative for us represents that change. So with that in mind, I'm differentiating then my equation, and this is what I get. Assuming that the total population is not changing, so no births, deaths, and so on, I get the right-hand side 0. And then in the left-hand side, I have these three derivatives. Now, we really need to describe an equation for each one of them. And these will be the equations for ds dt, di dt, and dr dt. And as we can see, if we sum them up, we're going to get 0. But let me just go back now one by one and try to analyze. So we can see that the change in the susceptible is proportional to the encounters between the susceptible population and infected population with this rate alpha, which we call it infection rate. And of course, the susceptible population is going down, so that's why I have a minus here, so that the change is negative. Now for the infected, well, for the infected, I have that change is proportional again to the encounters between the susceptible and infected population with the rate alpha, but now positive because the infected population goes up. And then also we're going to take away with the rate beta, which is our recovery rate, a portion of the infected population because they're going to recover. And then dr dt is simply, proportional to the infected with some rate beta, which is the recovered rate. So as we can see, when we sum them up, they're going to equal to 0. And this is what they are defined in the most basic way. Of course, this doesn't account for everything that is happening, in the communities and so on, but it will give us a flavor of how the population of susceptible, infected, and recovered are changing in time. So let me talk a bit more about these rates, about alpha and beta, because those are our data, those are our parameters now that we need to have values for them to be able to run the model. Well, alpha is that daily infection transmission rate, beta is the recovery rate. So they act, as we can see in the equations, to control how fast or slow the members progress from infected into recovered and from susceptible into the infected. Now, beta is roughly the reciprocal of the number of days an individual is sick enough to infect other. That's what is taught into this epidemiological model here. And we have this composite parameter, if we look at it, alpha over beta, and which is called the contact number. So alpha over beta, I can write as alpha times 1 over beta, where alpha represents then the number of close contacts per day per infected, and 1 over beta, being the reciprocal of the number of days an individual is sick, is the number of days being infected. Okay, so if I multiply this 2, that means I'm getting the number of close contacts per infected individual. And this is something that can be estimated for every type of epidemic situation or even pandemic situation that we have here. It can be estimated. Beta also, it can be estimated. Then alpha can be computed, simply as gamma times beta. And this is how we get our hands on some of these parameters. Now, having these parameters, these equations, the system of our SIR, which is the basic, as I said, model for the spread of the disease, can be simulated. So with that in mind, we can obtain our functions because now the solutions are functions. So I have a function for the susceptible population in time. So my x-axis is time, so I see how the susceptible are moving in time. Then I is the infected, the function of the infected population in time, and R is the recovered, the function of the recovered population in time. And I have here some specific constants that I picked. So for alpha, we have 1.3, and for beta, I picked 0.2. And this might be better if I try to simply run it. So if I go here, and let's see here. Okay, so we have we're inside of an applet here, so we can animate and you can see at a specific time how these numbers are changing. So how the recovery goes up, the infection goes down, the susceptible go down as well. But at some point, which is around like here, for example, around 4 days, we can see that that's when we reached the maximum for the infected population, and afterward it went down. Okay, so this is then this model SIR that was used even to model, measles and some other diseases during the history. Now here I have another like applet, and from this one here, what we can see, and I'm trying to point out, is that we can play with some of the numbers. So we can see that the contact number, I set it to 5. So it might be small on your screen, but the contact number is 5, which helps us finding that alpha and beta. And then the duration of infection, I put at 14. And these are pretty reasonable numbers for our COVID-19 to do. And then initially infected, I put it very low, like 0.05. And initially immune, this I put it very strong, like 65% of the population, so that we can try to see what happens like when this vaccine, let's say, kicks in, and then this initially immune population that we have is much higher. If I go very low here, for example, 0.8, we can see how the infected, it will grow. You're going to have this growth into the infected population, and then it will slow down. But if you start with an initially immune population very strong, there is not much of a growth, very light one, and immediately dies down. So what happens is that reproduction number, also known a lot and used in literatures these days, even on TV, you hear it. If it goes less than 1, that means that in my derivative, that change of the infected population is simply becoming negative, so it will die out. So this is this comment on the side here. Now, if I go back to the presentation, Next, what I want to go into is something about my research. So these days we have different type of modeling, and we can almost now group it into two, different categories. One being like data-driven, and the other one which is model-based. So data-driven, when I say it's more the one where you are using data, there is like now this deep network, neural networks, modeling. Model-based is the one that is more based on conservation's law, first principles of physics, and so on. So you get equations, and there is a bridge that is happening these days between these two. And as the news from the SIAM, our Society of Industrial and Applied Mathematics, very recently, January, February, is saying how computational methods for partial differential equations or differential equations still remains a vibrant research and area whose open challenges will include these efficient solutions to find to nonlinear coupled systems and partial differential equations, and even in 2, 3, and higher dimensions as well. So this is where my research really lies in these computational methods for differential equations and partial differential equations. So with that said, like, why do we really need them? Okay, so if you try to solve for that x, because that's what math is, right? So x plus 3 equals 5, very easy, you know x is 2. But if you have cosine of x equaling to 0, well, maybe we're going to have to remind ourselves of some unit circle, you know, some trigonometric things, and find the solution how you have infinitely many, it's pi over 2 plus a multiple of pi will all satisfy this equation. But if we try cosine of x minus x equaling to 0, this is much harder. This is where pencil and paper cannot help us anymore. And this is where computational methods, numerical methods will come into place. And some of them have been, developed from a long time ago, but they have been, improved over the years, and especially with the growth of the computational resources that we have nowadays around us. This is a very vast area and very rich now, and lots of researchers are working. So one of the older methods is this Newton's method. So this is just then how you can solve, for example, if you have a more complicated, what we would say nonlinear equation equaling to 0. Well, you're going to look at the tangent lines, and you're going to find then these are lines, so you can easily find their intersection with the x-axis, and those intersections with the x-axis of the tangent lines are your approximations of the root. So we may not be able to find the exact value of the root, but very close one, yes. So with that in mind, now let's go into the computational fluid dynamics. And what is that all about? So we started with the modeling of a very simple function, linear function for electricity bill. Then we have a system of ODEs, what we say differential equations for the SIR model that models the spread of a disease such as COVID-19. And now if we go into fluid dynamics, this is where we're going to see models based on partial differential equations. Okay, why fluid dynamics? Well, it has applications, so many, like engineering, the engine combustion, biophysical one, the blood, the blood flow, in our veins and arteries. Then climate applications, weather forecast. This is where these partial differential equations are coming into play. And as you can see in this picture here, we have an airplane, and at the tip of this wing, we can see a very big vortex that started to be created. And its creation really lies at this tip in a very thin layer around the object, around the airplane. So understanding this flow, which is very turbulent, what we say, around the object, around like an air jet, and so on, is very important, because in those thin boundary turbulent layers is where the drag lives. And the jet uses half of its fuel just to overcome the drag. So understanding this flow and controlling the drag will help us reduce the fuel, will help us reduce bills, will change economy, and will help us reduce pollution, will change the environment, and so on. So what if we could catch the wind or calm the seas? Impossible might be, but researchers are investigating natural phenomena. And one of them that I have been studying is turbulence. So what is really turbulence? Well, von Neumann said that there is no sense in being precise when you don't even know what you're talking about. So turbulence is a very complex phenomena, and it's really hard, and we still don't have a precise mathematical definition from it. The way it's defined, usually in the textbooks and so on, is by listing its characteristics. The turbulent flow is irregular. You have lots of change in space and time. You know, when you look at these solutions, it's diffusive, rapid mixing is happening. Then we have the so-called Reynolds number that appears, and usually it's very high and gives us lots of trouble. And then we have this three-dimensional vorticity, you know, that it's coming into place, those vortices like that I just showed you at the tip of the wing. Then it's dissipative, and then we have this characteristic of the continuum as well. That whatever happens at the small scales, also at the large scales, is preserved. Okay, so how is this flow simulated? Well, it's using the so-called Navier-Stokes equations that are known around like for a good century, but we still struggle with the mathematical analysis of it. We cannot prove the existence of the solutions of these equations. For 3D existence of the strong solutions, we know the uniqueness, but not the existence. And then we can talk about so-called weak solutions of this system of equations, the so-called Navier-Stokes equations. We cannot talk about the uniqueness of the weak solutions. So the weak solutions, they exist, but we don't know if they're unique. Then the strong solutions, we don't know if they exist, but we can prove that they are unique. Well, what are these equations? The first one comes from the conservation of momentum. The second one is from the conservation of mass. So from physics, describing physical processes that are happening in the fluid. And this first term is the change of the velocity in time. So U here represents velocity, P represents pressure, F is some body force that drives the flow in this application. 0T is my time interval, omega is the domain on which I'm solving these equations. So this term represents the time derivative. This is like a so-called nonlinear term that gives us trouble. For the Navier-Stokes equations, this is the viscous term, mu is the viscosity here, and P, as I said, is the change of the pressure, and then div of U is the incompressibility condition that we have here, that the fluid cannot be compressed here. So what appears like when you non-dimensionalize the Navier-Stokes equations, you get this Reynolds number that equals to LU over nu. So L is and U are some reference length and velocity, nu is the kinematic viscosity. So if the viscosity is very small, the Reynolds number would be very large. And this is something that happens for us a lot in the nature. So Reynolds number is something that drives the flow. So when we have turbulent flow, Reynolds number is very, very high. So you can see for airplanes, the Reynolds number is of order 10 to the 7. Atmospheric flows like geophysical flows and so on is 10 to the 20 even. And this gives us a little bit of trouble. Now, I'm going to take a second and I'm going to show some of my simulations where we can see the influence of the Reynolds number. So here is a simulation. We have a flow in a channel. It's enforced from the left side going towards the right side. It hits this obstacle, this step, and you can see it creates here a vortex behind the step, and it's just one. And the Reynolds number for this flow was equaling to 1. So we have only one vortex here behind the step, as we can see, and this is Reynolds number equaling to 1. Now, let's say what happens if I put a different Reynolds number. So how about 600? So which means the viscosity changes of the fluid. So the flow again comes from the left side, hits this optical, this step, but now we can see the creation of these vortices here. And this is the interaction of the flow with the obstacle, and we can see how it creates and sheds these vortices, a big difference. And this is where, in these layers, very close to boundaries, is where the drag and lift lives, and they are very important for us to be resolved correctly. Okay, so now if I go back to the presentation, the next thing is, so after seeing those simulations, for different Reynolds number, let's see what is the good way, to simulate this. Well, you can use Navier-Stokes, but for that we have a theory that says that you have to do a very small mesh, what we say when we do numerical methods, and that requires very large computer resources. So then one way is to do large eddy simulations, where you're looking at large structures, and hopefully that will help then model the influence of the small ones onto the big ones. You need less computer powers for that. Okay, so then how do you do? Well, you're going to filter your Navier-Stokes equations. You're going to close somehow the models, close the equations, and based on the way you close those equations, you can get different models. So one model that I work a lot is the so-called time relaxation model. So as you can see, very similar to the Navier-Stokes equation, I just have this extra term here, the one that will induce some type of an artificial viscosity and will model the influence of the small scales up on these large scales and so on. So this is the term that represents these generalized fluctuations and so on. Bar represents here the filtering using this differential equation that we're using to filter. Okay, so then let's go into some numerical analysis and computations with this model. So what did we do? Well, the most important thing is the energy. So you want to make sure that your model, has a very good this energy balance, what we say, and this is the energy balance written here mathematically with symbols and so on. So what happens here is that if there's no body force, if F is 0 and if chi is 0, your coefficients, mu viscosity in the absence of the viscosity, then we have that the energy, this norm of the velocity at any given time t is going to equal to the initial energy. So the energy gets preserved, what we would say. So there are lots of talking about this, so how the energy cascades from large scales into smaller scales and so on until it hits viscosity. And Kolmogorov, this big Russian mathematician, he worked a lot on this theory for the energy and understanding what is the smallest scale that appears, the smallest vortex, rotational structures that appears in the flow. And he gave some results for all that stuff in his famous K41 theory, which was written during the Second World War. So 41 comes from the year 1941. So all this math that was here, later, let's say in the 40s developed, it was earlier in the 20s observed by Richardson, but he just had a very poetic description of it, saying how big whirls have little whirls that fit on their velocity, and little whirls have lesser whirls, and so on, that goes to viscosity. At the end, where the energy then gets transferred into heat. Okay, so leaving all that now on the side, let's look how do we solve that system of partial differential equations, those Navier-Stokes equations, or my model, the so-called time relaxation model. How do I really solve it? Well, one method that I use the most is the so-called finite element method. And this is really the mathematics of it behind it. This would be the finite element formulation of it. We create these spaces that we have here, and then we multiply by a test function our equations. So we integrate. So these parentheses really represent integrals over the domain, what we call inner products. Then here, this is a fully discrete scheme. So even the time derivative is discretized. That's why we have here that this hat represents the average of the velocity at the specific Tn and Tn minus 1. So it's like current time step and previous time step. This is the way the nonlinear term, it had to be treated in a specific way, so it doesn't contribute to the energy dissipation because the nonlinearity should equal to 0 the way it does for the Navier-Stokes equations. So having all that said, we get this. We get this finite element formulation that we're going to use to find our solution. Now, said even more, this finite element formulation that it's here really breaks down in solving a very large system of linear equations for sometimes even 100,000 unknowns, 200, 500,000, and so on. Here depends how big of a computer power you have to go into and so on. And this entire thing then actually really breaks down to solving a type of an equation. How was that first one that I showed you in the modeling with the electricity of the electricity bill and so on, but we don't have only one unknown x. Think I have 100,000 of those x's that will, you have to solve for if you know your y, for example, and so on. Or so this is in that context set. Now also mathematically, I can say, okay, I get like a system, I have my matrix, which is very large, and we have problems with that matrix, that it's not sparse, so we have to, we have to allocate the memory for it and so on. Okay, so after that, having this, and before I even try to solve it, I really want to make sure that my iteration is computable, what I say, that the solution exists. So this is where we go with pencil and paper, and we really show, mathematically that the finite element variational formulation does have a solution. So we have the existence of the solution, and it makes sense then to compute it, to go for it and to compute it. And this exists for the existence, the stability bound, such one as it's written here. It's very important that we have in some norm, the velocity is bounded by my data, which is the body force, F, or initial condition, U0, here and so on. So that means that if I have some change in my data in F, initial condition, that my solution will not change by much because it's bounded. It's less than or equal than this stuff here in the right-hand side. And that's very important. And we can look into that even more through some kind of a sensitivity analysis that can be performed. Okay, how about now, after you know that your solution exists, you are going to compute it and so on. The idea is that the computed now solution, it will converge towards the true solution of the model, or the solution of the Navier-Stokes equations. So if we go back to that Newton's method picture that I showed, is you want to see how you are going towards your root on the x-axis. You're not going away from it. So these kind of estimates that I have here, again, pencil and paper, this is where we take and we show them that this solution that really the computer will compute for me tends to the true solution of the Navier-Stokes. I'm not just solving for something that it's not meaningful. It's a meaningful convergence that we have here, convergence towards the true solution. And there are lots of parameters, of course, floating around for us. And there is this age, the mesh size, delta t, the time step that we are taking. So if we let those ones go to 0, then the right-hand side will go to 0. And in the right-hand side, what we have is also this function f that is defined by all these norms here. But everywhere we have powers of ages and a delta t. So that will go to 0 as well when we let these two quantities, the delta t and age, go to 0. So we have now all this nice theory in the background. I have this model. I discretized it, some numerical method implemented. I showed that the numerical solution exists, converges towards the true solution. So I'm ready to compute it and then to look at the simulations as well. So here are some simulations for the 3D so-called step problems. So you saw that simulation of mine in 2D where the flow hits, the obstacle, that step, and then a vortex gets created. So this is now in 3D, and there is a slice that is presented here. So the flow goes from the left towards the right, and again, you have a rotational structure that appears here behind the step. So what we want is, we know that Navier-Stokes will give us trouble unless we go with a very, very fine mesh, and that's not feasible for us. That's why we'll look into these models, in fluid dynamics. We'll look into different types of modeling, stabilizations, regularizations, what we call the Navier-Stokes equations. So one such model is the Navier-Stokes alpha model. And so the next slide will give you a zoom in behind the step, what's going on. So these are some string ribbons here that they represent the way the flow moves behind the step, so we can see this rotational structure, and this is where that drag and lift, as I said, lives when it comes. So this is a coarser mesh. So now we are challenging our model on a coarse mesh with less computational power. Is it possible for us to obtain these rotational structures? And we got good results here. Now, before I go into conclusions, so let me show another simulation. So here we can see a different one. And this is the flow enters from the left side, it hits this obstacle, and you can think of this being just an airfoil. It has a more circular, form here, but it's like an airfoil, air jet, and as it hits the flow, it creates this vortex street, what we say behind it. This is the famous von Karman vortex street for us, the benchmark problem, so the models will have to show something like this. And then here behind the step, so if I go again, behind the step is where we can see the formation of the rotational structures, and this is again where that drag lives. And aerodynamics and the fluid dynamics is a lot about the computations of the drag and lift. Okay, so this simulation was done really with the Navier-Stokes equations here, and then we tried to use our model and show that we get the same thing by using less degrees of freedom, what we'll say a smaller mesh. Now, let's see what can we say about some conclusions. So all models are wrong, but some are useful. So this is the famous quote of the statistician George Box. And as strange as it sounds, you know, probably it is true, because just the complexity that we have in the nature at this moment is really impossible for us to get that perfection in a model. But that doesn't mean, you know, that we should not do it, because every single model might be wrong, but meaning that it will never represent the real behavior. But on the other side, if a model cannot describe exactly the reality, it will still be extremely helpful if it is close enough. And, you know, we may not be able to describe the flow around an air jet, but air jets are still like flying for us. So these simulations are very useful, because sometimes they can cut, you know, bills from modeling things, or like just overall, it can give a prediction, you know, of something that may happen, and based on that, you know, decisions, important decisions can be made. So again, even if a model cannot describe exactly that complex reality that we have, that harmony that is around us, you know, on an everyday basis, it can still be very helpful if it is close enough. And this being close enough, this is where math comes into play, and this is where math shows how close we really are. These are those norms, those theorems that I showed, that to say that we have the existence of this solution, and that this solution tends to the true solution using mathematical, methods and mathematical tools to back up our closeness to this reality that we have. So with that being said, I want to finish then what mathematicians use to describe mathematics, you know. So it's imagination, curiosity, discovery, and this is starting with the old Greek civilization, exploration, game, invent, and truth, ask, free. And I think this, it's not that we should, you know, find them in math, but I think we should find them in every science that we do in our everyday lives. And I thank you all for your attention, for listening, and I hope I provided a glimpse into these exciting mathematical activities and opportunities. So I think I'll finish here, you know, and see if there are any questions in the chat that I can address.
Thanks so much, Dr. Neda. That was amazing. And honestly, I'm going to be completely honest. I am not a mathematician at all, but it made a lot of sense to me, and it was very concise and very clear and very informative. So thank you very much.
You're welcome.
It looks like there is a question in the chat from Steve Jones. And can you see the chat, Dr. Nader, or do you want me to read it to you?
No, I think if I stop the sharing, then, I can definitely see the chat, or give me 1 second, I should be able.
Okay.
So here, so since turbulence occurs at all scales, there must be vortices smaller than any given mesh size. So in what sense do discrete solutions converge to the true solution? Yes. So I think I understand the question from where it's coming. So you have these vorticity rotational structure, but this is what Kolmogorov theory says, that size of those rotational structures is proportional to your Reynolds number, and to the inverse of the Reynolds number. And with that said, you can approximately, calculate it. The thing is that it's very small, so you need a very small mesh size. And to go then with that mesh size, for us, sometimes it's simply not feasible to do it in computations. So what we do is, as I said, then we tend, to model the larger structures, larger ones, and get those ones done, but with such like a modeling effect that the small ones are the effect of the small ones is incorporated into the model. So now when you think about the convergence, when you are going to let your delta t, the time step, and you're going to let your mesh size h go to 0. So when you do that, then you are going to be able to capture them all, right? So in the convergence analysis, the idea is that if I take just smaller and smaller time step and smaller mesh size, I should be able then to capture all these structures at every time step. Now you are going to be restricted by your computer resources, so you won't be able, to go as small as you probably would like. And on the other thing is not just like computer resources in the sense that the mesh size is something that you are like, restricted by. It's also sometimes we want to simulate long enough in time. Let's think about the weather forecast. So weather forecast is calculated on an everyday basis. So if they have to announce it for tomorrow, let's say what it is, and they want a precise one, well, you have to make some kind of an optimal estimate here. What should be your mesh size? What should be your time step? So that you compute that solution within a time frame, so that the solution is computed, it's done, and it can be announced to the public in news and so on. So there are like here, how should I say, you have to play around with lots of parameters that are coming into play when the simulation is really done. And as you can see, the weather forecast is so clear and good that we get for tomorrow. But if you look at something that today is given for us that will happen, let's say in 2 weeks, well, as we get closer, we're going to see that there will be some mistakes in the temperature and maybe in the wind and so on, because the solution gets polluted in time. So as we run the simulation, in the first few time steps, we're going to get a more accurate solution. But as we move more in time, the solution would get more polluted. So that's why we cannot trust the weather forecast so well, what will happen in 2 weeks exactly. But still, we're pretty close enough. So those temperatures are not going to change so much in 2 weeks. We know that we're not going to have over 100 degrees in 2 weeks, most likely. And, this is true. So these models are not, cannot give us perfection, but they can really give us very useful information. So great talk. Thank you from Michael. Are you solving for space and time simultaneously or stepping space forward in time? So I'm solving for the solution in space at every time step. So it would be like, even those systems of partial differential equations, they become like a system of ODEs after I hit it with the finite element. So I'm solving that solution in space, like the space distribution of the temperature, velocity, pressure, whatever we're solving, and at a specific time, and then I move with the delta t in time, another delta t further down the road in time, and so on. So that's the way this gets simulated. So, so thank you, Spear. I'm reading like the Dr. Spear comment. You're welcome, and I'm I managed to create such an encouragement for you. And I think somebody has his hand raised, if I'm not mistaken, Corey.
Let me see.
Whether it was by mistake or not. So, I mean, that's fine. I can accept questions even like.
I didn't see it, but if you have a question and you want to ask it verbally, you can unmute your mic and ask Dr. Neda as well.
No, I did not find. So Steve Jones, I did not define like in this talk precisely what are those strong and weak solutions. So the strong ones would be solutions of the PD, the system of the PD, and the weak solutions would be solutions of the variational formulation of the system of PD. And, this is the $1 million Clay Prize, all about it. Like you have those few open problems by the Clay Institution. And this one in fluid dynamics about the solutions of the Navier-Stokes equations is one of them. And that's where they, if we can prove those ones, so we can get some prize money, I assume. This is a question for many, many years. And there is a struggle to do it. My contribution mainly in this area is from the computational point of view. So I'm looking at these finite element solutions of the Navier-Stokes equations and the models like in this fluid dynamics or large eddy simulations area, what we call what we can do about them mainly. But it's very important for us to know because, if I'm even trying to find a solution to a system that I don't know if it has a solution, that's not good either. So it's very important, to get the bottom of the existence of these solutions. So that was a very good question, Steve. Yes, the $1 million question of the Clay Institute. So Harold, thank you, Harold, for the nice words. You're welcome.
All right. Thanks, everyone, so much. We'll give maybe another couple seconds to get a question in case you're typing something. But it looks like they've kind of slowed down a little bit. And I think, Dr. Neda, if you also want to include your email in the chat, if you're comfortable doing that, sure. People can email you with any questions that they might have that they just didn't get a chance to ask. Feel free to reach out to Dr. Neda. Again, this presentation will be on the College of Sciences YouTube page and will also be available on the College of Sciences website on the virtual lab notes page. Looks like a lot of great kudos, and it really was an excellent presentation, Dr. Neda. Thank you so much for your time and for your effort and for spending some time with us today. And thank you to everyone for coming.
No, it was my pleasure, really. So it was very nice to share all this with you after being with me for so many years.
Thanks so much.
You're welcome.
I'm going to stop the recording. Yeah.